Now we're going to look at getting an equation or a value for the moment of inertia. So the objects might just be listed on a table we have in our book on page 291. These objects might include a disk, a ring, a solid sphere, or a hollow sphere, and I can just look up what is the equation for the moment of inertia and plug in, say, the mass or the radius of my object or the length. Secondly, we might have a point mass. If we have a point mass, the moment of inertia is just the mass times its distance from the axis of rotation squared. If I have multiple points, I just add up each of their moments of inertia to get the total moment of inertia. If I have multiple objects listed on my table, like a wheel with spokes, for instance, here I have a ring, and then I have some spokes, which would be just single rods, which is also on my table. And all I have to do to get the moment of inertia is to add up the individual moments of inertia. So from my table, I found out the wheel itself is like a ring, so it's mr squared. The spokes, and you'll see I did them in different colors here, have the moment of inertia of a rod. And so if I add up all of those moments of inertia, I can get the total moment of inertia. And then our last object is if I have a uniform rod. Now we do have the uniform rod as 2 moments of inertia on our table, but what if we want it at a spot that's not listed? What if we want our moment of inertia to be somewhere else? And so in order to do that, we're going to have to take an integral. And so we'll integrate it from its left end of the rod to the right end of the rod times x squared times the linear mass density, which is a constant. It's the density of our rod times the cross-sectional area, dx. And this will produce a I value for the axis of rotation at x equals 0. And so we'll see how we actually use that later on. And so what we're going to do now is we're going to go ahead and we're going to do some example problems with objects listed on the table, point masses, multiple objects, or uniform rods.